Okay, so I'll start. First, let me. Okay, so did you do the exercise that I had asked you to? Has anyone has? Done it? I had asked, for example, so let's take this. It's maybe too small, slightly bigger. Okay, let's take this example. Here's the one that I used. Okay.
Sir, I actually still don't get why the formula is linear in size of k.
Okay, that's what I'm getting. One step at a time. Okay. So first, in order to answer that question, first you should be doing. I wanted you to do a translation, a BMC translation for this formula. Okay. So then you would get some idea of why through sharing, the claim there was that through sharing, you could get it to linear. Okay, so that's why I had asked you to spend some time in applying the translation, recursive translation scheme I defined last time to this example. So I'm asking you the question. So did you try doing it? Okay, let's suppose, so obviously the answer is no. So if you don't do the translation, how can you answer that question? Okay, so let's try to do it here. So how would you start with? So the path I'm asking you to do for was, say, S0, S1, S2, S3, it doesn't matter, okay? So let's say, I mean, it doesn't matter even for this example or not, okay? So let's take this. I mean, it doesn't matter whether, so I'm taking the path. Given a path, and suppose I'm looping back to S1, okay? So this is a lasso from S3 back to S1. So I will get you the translation slide. Okay, this is a looping path. So you'll get a translation of this kind. So how do you start with? So you would do from 0 to 3, correct? So So you would have, yeah, so you'll start with 0 to 3. So I being 0, k being 3. Okay. So that let me write it as 0, 3 here. And here the looping path is to say S1. S1 or am I doing S2? So we want to do the same thing as it's okay, S1, so say it's 1. So we start with this. So what is this equal to? Okay. So the outermost operator is G. So what does the translator say? If it is G, then you have to do the minimum of L and I. L is 1. Therefore, what does this expand to?
So when we're saying 0 to 3, we're setting k to 3, but the path length is 5. Shouldn't k be set to 4?
1, 2, 3, 4. Maybe I should have said 4, 3. No? 1, 2, 3. No, it's the path K is, the K is from S0 to S3. That's my path. The backward, the KL loop is here. K is 3 because 1, 2. Can you see my cursor? 1, 2, and 3. So the loop back path is from S3 to S1. Okay. So K.
Okay, yeah.
Yeah. So you see how I showed the loop here. Okay. See, that's why I had asked you to put some effort in actually doing it. So then I can do it. I mean, otherwise, this becomes like a, school lecture. So where I'll have to do everything. Okay. In any case, so that is, these are the kinds of details that unless you do it, guys, you won't get it. And then you ask this question, why, how is it linear? Yes, but it'll help if you do something, okay? So K is 3, that's why it's 0, 3, and L is 1. So you got it, Diganta?
Yeah.
Okay. Okay. So this is like, what does it expand to? So it's a conjunction of f of g of p be something like 1, 0 dash 3, okay? And the 1 is just saying, okay, it's a lasso, okay? So at 1. So you got it? You're up to, you with me up to this point? Yeah? So this is how you recursively apply. So then it is F, okay? So what will happen is this will now, it's a conjunction. at the topmost end. So each of that will then become a disjunction, okay? A disjunction of, that is F. F is once again a disjunction, right? So it gets translated disjunction. So it will be something like this. If it were not a looping path, then it would have gone all the way to that. Now here, I'm just taking, yeah, so I'm just taking from I to, all the way, J is minimum of L and I. So because there is a tail, therefore I'll take it from there to K, okay? So this will be a disjunction, something like this. So I'm expanding the first part here, okay? So that becomes 1, dot, 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 okay? There'll be 4 disjunctions there. Now, what will the second one be? Okay, so I'm expanding the second part, okay? So look at that. If I expand that, that will be, it'll start from 1, okay? Correct? And then it will go to 2, 3, and so on, okay? So you see immediately here, there's so much, okay? Then you get 2, 3. So the 2, 3 will expand to 2, 3, and 3, 3. And 3, 3 will just expand to a GP of 3, 3. You see the sharing here already. So the GP of 1, 3 already appears inside GP of 1, inside the first disjunct, okay? So, and that's how. So if you expand the whole thing out, it gets like a tree form, and you will see, just like, a BDD, there is a lot of sharing, okay?
But my point is that when we write a formula, the form, I know that there is a sharing of formulas, but still when you write the whole formula, that the length of formula will be exponential, right?
Well, unless you write it, you won't know. So here is what I'm writing, okay? So let's look at that. This is a complete expansion, okay? So here, solid edge, the node from which is all solid edges, they mean and, okay? This is an and or graph, okay? So the first one is an and of these things. So all these things are part of it, okay? So then the next one is dot because it's or, and then it is and it terminates at PS1, PS1, PS2, PS3. And you see that each of this is now completely part of the second node. All the subterms of these things are part of the second, some part. So if you completely share it, you look at what is the length at each level. Okay, the depth of this thing is the depth of the formula. And at each level, it only goes up to K because of the sharing. So if you introduce these as, one way to view it is as these are, yeah, so that's why. So it is, so the formula is linear.
Yes, sir. But what happens is the formulas which are sharing are repeated multiple times in the actual formula which we get at the end.
No, but why? So suppose I make these as variables. At each point, I introduce new variables. See, so at the end, what is happening? I'm getting PS0 and PS1 and PS2 and PS3. The next thing is just PS1, PS2, and PS3. Okay. So if you just equate them to variables, you could introduce more variables, but each variable will be equated to at most k-long formulas. Okay. So why do you have to expand it out? I'm saying you don't need to expand it. Now, I don't know if you guys attended my talk on the Cyton expansion, okay? You remember that, at least I discussed that in some of you, I guess all the people that are attending today did attend my SAT solver talks. Did you guys? Hello? Is that a yes or a no?
No, sir, I did not.
Okay. So, yeah. So, I mean, I can show some slides. I thought some of you attended them. So there, see, it is something similar. There, when you try to convert a propositional formula into CNF form, in general, you can have a blow up, but you can introduce variables. Okay, so here, consider that this one is, suppose each node here, I introduce a new variable. That is equal to this variable and this variable, the second one, and consider each of this thing as a new variable. Okay, so what is this? Okay, this variable is equal to this and this and this and this. That is 4 long and. Okay, now this one is a 4 long or. Okay, and this is similarly, it's a 4 long or using the same variables. Okay, and here also it will be new variables you can introduce. So which will be this variable will be PS0 and PS1 and PS2 and PS3. This one will be once again the same thing, PS1, PS2, and PS3. So you do not construct new formulas, okay? So as you recursive, this will be implemented using recursion. And if you equate, you introduce new variables, propositional variables that will be equated to this conjunction or the disjunction, depending upon what you have, of a bunch of things. Okay, so when you do this, this will be constructed, as just a conjunction. I mean, at this level, this is just this is a conjunction of this, and this one will be at this level. This will be a disjunction of all these things. Okay. So if you introduce new variables, each variable will be equated to some disjunction or conjunction of the variables at the next level, and that conjunction will only be k long. Okay. So literally you will have to introduce new variables, and the number of variables we'll be introducing will only be linear in the depth of the things. Okay. So yes, you will have to introduce new variables. You won't be literally, if you literally substitute and then get a CNF, that will be exponential. But by introducing new variables at each level, which will then be, this GP3 will be this, and GP3 will be, for example, it's PS0 and just GP of 1, 3, okay, because which is an and of these things. What is GP3? It is PS1 and GP2. What is GP2? It is just PS2 and PS3, and GP3 is just equal to PS3, okay? So if you introduce new variables to denote each of these nodes, yes, you will be adding new variables, but the formula that they are equated to will be at most k long, okay? Disjunction or a conjunction of k sub variables, or at the end you will have these atomic predicates, okay? So that's how you will have to translate. Anyway, you have to write a recursive procedure, and then you will see if you've already, for example, when you expand, you just first say GP3, this node here is equal to PS3. Now, this one, when you expand it, you will notice that it is PS2 and GP of 3,3, which you already have, okay? So it'll be that and that variable, okay? The next variable. What is GP of 1,3? It is PS1 and GP of 2. So if you already have introduced a new variable for that, then you don't physically substitute. You just have to check during a recursion thing that you would have already generated a formula, and you introduce a new variable. That's what you put it in a table, okay? So, and the table will be just equalities of formulas, each of which is an equality of a new variable equated to a formula, okay? So GP3, if you expand it, it will be PS0 and GP of 1,3, which is once again has been introduced as a new variable. So that's how you get that sharing, by introducing new variables with equality. Okay, there'll be extra variables, but you won't physically substitute. You will keep them separately as somewhere equal to that expression. Okay, which is a disjunction or a conjunction of at most k long. Okay. Similarly, here also it's the same thing, because if GP of 0, 3, when you expand it, it will be these things, but then it will already contain, this one will contain the rest of the things, okay, as subformulas. And if you introduce a new variable to equate that, then you will not be getting the full explosion will not be there, okay? So, question number 1. Do you see there is a lot of sharing? Yes or no? Can someone answer? Shall I take that as a yes?
Yeah.
Okay. And of course, the couple's question was good. So if there is sharing, how do you exploit that sharing? Was the question, and that is by introducing new variables, okay? And that you equate to, the formulas at the next level, and then you will of course add new variables, but you shouldn't be physically substituting in the formula. Then you don't get sharing, okay? So, and the sharing is kind of simulated by introducing new variables and making them equal to an expression in terms of the other variables at the next level with the thing. Okay, so that's how that you do. Okay. Yeah, the concept is similar to that. That's Cyton encoding. So maybe I don't know if I should show you that or not. So this, anyway, you have to implement this using recursive function. See, this is and then when you do that, all you have to do is to create a table, okay? You will go down all the way to the recursion, then you will see, you will do this, and you have to store that in that table. And then when you expand this, you will see that if there is already a variable, this is already generated, GP33, which is actually part of GP23 because GP23 is PS2 and GP33, okay? Therefore, you already have that. So you don't need to generate it. You could just keep that as a variable. Similarly, GP13 is PS1 and these two. So you can keep that, okay? If indeed you have stored in the table. So the table will have a bunch of equalities. But what I'm saying is the equations, the right-hand side of the equation are of at most k long, okay? So that is what by that I'm saying, yeah? And that you can do. So in your recursive thing, see, this is a standard trick that this is caching, okay? When you implement something as, sometimes it is used to reduce the number of recursive calls because when you use recursion, it's always exponential. The number of recursive calls that you get is exponential, okay? And people, although they write programs, they rarely do that because otherwise you will be invoking an exponential number of recursive calls, okay? And in all this BDD, all the BDD operations, etc., that I've shown, they all are done recursively. And it would be a naive implementation to just implement it using recursion because then you will have 2 to the n recursive calls. So the standard trick that is used in functional programming languages, I'm sure you must have gone through this in basic Haskell and so on, is that you do something called caching, okay? So before you invoke if you store the result of the next recursive invocation in a table, then before you actually do the invocation, you will check if the results for that is available for that argument that you use in a recursive invocation. If so, then you directly take it from there and you don't use, you make a recursive call. And that's what is caching. So here you're actually, what I'm doing is caching those things. Basic, programming 101, that is, okay? And here, the structure of the formula is such, there is a lot of automatic sharing, okay? And the way that you exploit that is to have a table. And that's what is, mentioned here, okay? You have to have a table, okay? And if they are, so then you could, and one way, easy way, don't get into hash table, etc. You just introduce new variables, okay? So it's in that sense, I'm saying it's linear, okay, for doing it. So you could, see, otherwise it becomes, yes, exponential. If you really literally plug it in, then the same thing will appear so many times, okay, which you don't need to keep by caching the sub-expressions in a table and then equating them to a variable, you could use them. Yeah, okay, so that's what I mean. So I hope you got some idea, okay? Kapil, you were the one who would ask this question. So, but this is generally applies to everyone. Yeah, this is the optimization that, what I meant. Okay, so I would like you to consider implementing, doing this optimization when you do the implementation, okay? So, okay, so if there is no question, I'll move on, okay? So I'm going to now start talk about bounds, okay? So Yeah, this is the first one. WCB theorem is a theorem that guarantees existence of a bound. Okay, if a formula F, I'm talking about existential LTL in LTL formula. If there is a path in M satisfying F, infinite path, if F, the existential version of the LTL, is true for the model, then there exists a bound K, for which F gets satisfied with bound K. Okay. Now this one is you could get it by in two ways. One, we will see in the next week. We will be looking at, that will be the last lecture, or at least the topic for the term, how LTL model checking, complete algorithm for LTL model checking by constructing what is called a tableau. Okay, in that method, LTL model checking is reduced to checking for paths. Existence of a path satisfying phi is reduced to exploring paths to a strongly connected component in a product transition system, which is constructed as the original transition system, the Kripke structure M, and then you construct a transition system for the negation of the formula. This is classical automata theoretic way of doing things, okay? And so where you take the formula, take its negation, you construct a transition system. That translation we will see next week. And then you take that cross product, and in that existence of a path to that satisfies phi is reduced to one of checking. There is a path to a strongly connected component. Okay. Now that one can show that the longest path to a strongly connected component is this long. Okay, it is. It is as big as this. Okay, the cardinality of the set of states, and 2 to the f. Okay, the reason you get 2 to the f is because this transition system, when you take the negation in general, there is an exponential blow up in the representation for the size of the transition system, and this can be used as a bound in the worst case for your K, and it can never be longer than this bound. Okay, and this is a path to a strongly connected component. Therefore, your lassos, which is what is being checked here, can never be. This is the most liberal bound that you can actually get for any finite state systems. Okay, so that's how you can in general prove the existence of a bound, a theoretical existence of a bound. But there are several other results that can be used to get much better ones. Okay, and these are some theorems. I will put in the references here. Okay, so that's missing here. So it has been proved a long time ago, 1985, that if you stick yourself to the subset unary LTL, that is unary operators, temporal operators in LTL, that is F, G, and X, then MC, the model checking problem of that subset of LTL is NP complete. Okay, and that kind of indicates that maybe for the unary subset, the subset of LTL, unary LTL, they must be in a more reasonable bounds. And exactly there is another result, which says that for unary LTL, formulas in unary LTL they admit bounds that are some linear function of either the diameter or the recurrence diameter of M. Okay, and we will see some examples of that. Okay, in the next few slides. Then there is another theorem. Okay, once again due to Beer, in which he reduces all liveness properties. Okay, any liveness property that is properties in the full LTL that are not liveness, in the sense that they could be using U, R, and F, not just G and X and X. So you can always reduce a liveness property into the checking of liveness property can be reduced to one of checking a safety property on a enhanced model, okay, by adding some states to M and then deriving an M prime. How exactly you do that, we'll not get the details, but you can reduce. He shows that it can be converted. The checking of liveness can be converted into M prime, okay, and by adding a few states. It is somewhat similar to general safety properties, not necessarily an invariant property. Invariant property you could check by just enumerating all the reachable states. And I had explained to you in one of the earlier classes that you can always do general safety property by adding a few states that remembers some history that is required to show the existence of a counterexample. So you can always convert the checking of general safety property into checking an invariant property on a enhanced transition system. By enhancement, I mean by adding more states. And this is somewhat a similar approach where the Beer et al., they show that liveness property can always be reduced by adding, by keeping track more information in your original transition system. Therefore, then since that is reduced to checking a safety property of whether some state is reached, so after you enhance that, then as you know, for safety property, the worst case bound is recurrence diameter, okay? It is the diameter of M prime, but certainly recurrence diameter is also an upper bound. Therefore, the recurrence diameter on this enhanced transition system, M prime, can then be used as a bound on the thing. So that is also a way to do, which is, so that's another approach that you could use as well. So any of these things, all these things require you to, but the two things to note is that there exists a bound, okay, and that theoretical guarantee is, in theory, that completeness is guaranteed by this result shown, described in the first bullet, as well as the third sub-bullet here. And another thing to note is if you stick yourself to F, G, and P, then you can always express the bound as some linear function of the recurrence diameter. And of course, that exact bound, that what that linear function is, it depends on the property, okay? And that we will see for a few examples. Any questions? Yeah, this is interesting because then you can, the second bullet result is interesting because then as long as you can compute the recurrence diameter, you can compute, in theory at least, for any transition. We can express that as a SAT up search problem involving SAT calls. And if you do that, then by analyzing the property, if you can come up with these sum diameters and this linear function. So at least for the subset of unary LTL, you will be able to do it. Now for others, of course, you will have to, the disadvantage of this method is that you have to compute a bound for every formula, because for every formula, the completeness threshold, that bound, can be different, okay? And for the full general LTL, it is in general, in the worst case, it can be exponential, okay? It can be an exponential function in the recurrence diameter, okay? And that's what makes this problem hard, okay? Even when you stick to unary subset, this recurrence diameter in practice for transition system can be very unreasonably large, in which case you won't be able to use these methods. That's why people started looking at inductive model checking approaches, which don't require you to compute this bound explicitly. And the starting of that was K-induction, followed by interpolation-based induction, and finally, what is the best available inductive model checking method, completely automatic method that exists, is the property-directed reachability called the IC3. Okay, and whether I will discuss that or not, I'm still not decided. But if we have time, maybe we can. But that is the motivation for people started looking into inductive model checking. But if you can, for small examples, find this recurrence diameter, then you can certainly use this, or you can continue to use this method in an incomplete way as bug hunting, as a bug hunting methodology. Okay, so yeah. So if you don't have any questions, I will move to discussing some of the examples for which you will look at what the bounds are. Yeah. Any questions? Yeah, I don't have slides, so I'll have to use my handwritten comments here. Yeah, I hope you can see it. Shall I make the font bigger? Maybe I'll make it a little bit bigger. I don't know how it will look. This may be too big. Oh, okay. Okay, so you've already seen, so bound for FP. So where P is a predicate, okay? So this is the initial diameter. Why? I will explain. See, when you start with trying to prove a GP property, a GP property is a safety property. So, and you saw, earlier we described that the bound, the tightest, the most precise bound for a safety property or an invariant property is the diameter, okay? And we had defined the diameter. So the diameter is and when you use this method, bounded model checking, what do you do? To check the safety property, you take the negation, and that becomes an FP, okay? And that's why the existence, so the bound for the existential showing the witness for an FP is diameter, okay? So that's why the GP gets converted to an FP, an F, G gets converted into F, and that's why you have this as diameter. So since P is a predicate, yeah, so in general, the reason, yeah, okay. So yes, see, the diameter is the maximal distance between any state that is reachable from from any one of the initial states. Okay, if you could remember this thing. That I had, okay? So this is exactly the diameter. So in each step, you get multiple states and you keep going until you have reached all the states. So that is the diameter. Why is that? Okay, so you don't need to, so the loser bound is the recurrence diameter, because when you, by the time the recurrence diameter is the longest that you can go without any state repeating before you lasso. So you would have you would have encountered all the states by the time you reach a diameter, and certainly by the time you reach the recurrence diameter. Okay, and therefore, and since you would have checked the predicate P for all those things. Once you reach that, you will not be encountering. It'll lasso back, and all the lassos would have lassoed by that time anyway. And therefore, and since P is just checking something on the current state, you don't need to look at any parts starting from that state itself, and therefore this itself, the diameter itself, is the or the recurrence diameter, which is looser than the diameter, is a bound. Okay, so yes, so the diameter is the point at which you would have encountered you have seen all the reachable states, and since you are encountering multiple states when you do a SAT check in each of these circles, so even though when you reach the diameter, they might not all lassos might have not lassoed. Okay, you could still conclude that is good enough, because you would have checked P on all of them. But since the diameter is very hard to compute, I'm going to be just speaking in terms of recurrence diameter. So that by the time the recurrence diameter, all of them would have lassoed anyway. So, and you would have also seen you would have encountered all the states that are reachable from any of the initial states, and therefore you would definitely have checked P. Okay, so if there was a violation, you would have encountered that, and if there was no violation, then you could say that that you have seen a witness to FP. Now for GP, diameter is no longer a thing, because you will have to wait until to show, the bound for showing the guaranteed existence of GP. You will have to, if you encounter for an earlier K, that is fine. But if you don't, if you go up to the K, then you can be guaranteed that there does not exist anything for a G of P. And that is, once again, because P is a predicate, all you need to do is to ensure that you have gone all the way, you have gone to a K which is large enough to have accounted for all the paths that lasso. By that time, every shorter lassos would have been encountered in your BMC checking. You remember that the BMC check for each K checks for all lassoing paths. Okay, whether GP was true or not. It will fail only if if it is unsat. It could still be. That doesn't mean that there is no path. There could be a longer path. But once you hit this recurrence diameter, you can be sure either you would have encountered a path with a SAT result, or if you don't encounter, then there does not exist such a path. And the critical thing is P is a predicate here, and therefore you can get this. So now the question is, when are the situations when the recurrence diameter in general cannot be a large enough bound? Okay, I will take there one example. If you combine even G with X, you will see that recurrence diameter is not good enough. Anyway, so this we had gone through, but I'm restating for FP and GP. I hope you are convinced that the recurrence diameter in the case of GP, and that is true for FP as well, because recurrence diameter is larger than in general diameter. The worst case diameter is as big as the recurrence diameter. That is a bound for FP and GP. Any questions there? Okay, none. Then I will. Okay, so let me put this on this side and move this here, because I want to use this example to show it. Okay, so consider this example, and let's assume the TS1 I'm looking for, okay? TS1 here on the left side. So let's suppose S0 not P. In S0, P is false, not P is true. S1, P is true, and S2, not P is true, okay? So assuming, not P, P, and not P again. So certainly it satisfies, there is a path that satisfies this kind of this pattern, correct? Not P followed by P, P, not P, okay? So for this transition system, I'm claiming not P, 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 not P, infinitely repeating in infinite number of times is satisfiable. In terms of as an LTL property, this is how you express. If you are in not P, then in the next state you can have P, and the next state you can have P. And if you're P, then you can either have P not P following it, or not P, P following it, okay? So that is true here, because if you start with not P, okay, then you have P, 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 because why? Why is that? Because you can self-loop in S1, okay, as many times as you want. In this case, if I iterate for twice in S1, then I can find a path that satisfies this pattern of not P with P, P, not P, okay? Because this, for example, S0, S1, S1, and S2 omega, that execution path here indeed satisfies this pattern, okay? Correct? Guys, yeah, yes, any doubt there? Okay, so I assume it's yes. But see, the recurrence diameter is, what is the recurrence diameter for TS1? Can anyone answer? What is the definition of a recurrence diameter? Can anyone answer?
Is it 3?
Yeah, it is the longest path, longest distance that you can go from, I mean, I'm talking about the initial recurrence diameter, from initial state without, without encountering any repeated states before you will, you can go without any repeated state, okay? So here it is 2, S0, S1, and S2, okay? That's because after that, you will have to lasso, okay? That is as far as you can go. So obviously, the recurrence diameter is not sufficiently large enough to show the existence of this particular path, because here you will require a path of length 3. You will have to repeat S1 and S1 twice in this case in order to show the existence of a path, okay? So the reason that GP and FP were bounded by the recurrence diameter was because, see, in general LTL, you will have to check, in order to check it on an infinite path, on especially nested LTL formulas, you will have to check the satisfaction of the nested at any particular level nesting in the rest of the path. It's a path property. Unlike a CTL property, it's you will have to check it on the states, the subformulas. Here you have to check it on the path, starting from that index, okay, at which on a sub-index, and that's why. And in some cases, see, in the case where the embedded predicate is it's simple predicate, like it happened in the case of GP and FP, you didn't have to look at a whole path. I mean, you were able to check P in that state itself. Whereas here, you have to check on paths originating from, because here the check of the embedded formula has some X's, okay? And here it's actually up to two embedded X's. So you might end up having to check from paths originating from some of the the suffix indices, and therefore, so that's exactly what is happening here. So you had to, the only way that you could get a path that satisfies this is you have to have with this system, you have to consider repeated states.
So here we are considering EG or AG. We are considering EG or AG.
No, EG. It's always EG. Okay. I mean, yeah. So yeah. Yes, LTL checking here with BMC is always existence. Okay. Because I told you right in the beginning, in the first slide itself, don't confuse with AG at all. It's all, for all is taken a negation, and then you only show, you reduce the problem of checking for existence of a path that's satisfied. Okay, existence of a path in the model. So I'm talking about EG. Okay, if you just use the recurrence diameter, then S0, S1, S2 is as long as you go. I mean, you cannot. So you will have to consider a path that is longer than the only path, the path that satisfies this. You'll have to consider something that is longer than the path defined by the recurrence diameter, and it's because you'll have to consider this one. So this is one path, because the path S1, S0, S1, S2 going back to S1 does not satisfy. This is not a path that satisfies this property. Okay. Therefore, yeah, when you have nested X's, yeah, in general, if you have nested things, your bound is no longer, it can be definitely larger than the recurrence diameter. And that you see by getting XXP itself. In this case, it is enough to go, to use recurrence diameter +1. But you know, in general, that is not even true. I'll show another example where, yeah, here. Yeah, I'll make it bigger. So consider this example. Now here also, I'm looking for a path that satisfies this pattern. It's the same thing as what I had there. Not P followed by PP of not P omega. But my transition system is a little bit more complicated. I have fixed the transition system such that you will have to consider. See, obviously, if you look at the largest lasso, this is the largest lasso. I mean, this is the. I'm sorry, this is not the largest lasso. This is the largest lasso without any repeated states. Okay, so if you could, I mean, let me first describe the transition system. It is this kind of, it starts with a not P state, goes to a not P, and then it loops back. Or from each state, it can go into a unique another state in which P holds good, where you can stay for an arbitrary long time, and then it goes back. And similarly here, like this, okay, and then it goes back, okay. And you will see that this is true of this, okay, because the path that satisfies has to go to this T naught, stay there twice, go back here, come back here, loop twice, go back here, loop twice, and then go back, okay? So the recurrence, the lassoing path corresponding to the recurrence diameter is this one, okay? The longest path that you can go without repeating any states is this one, where you go from here, bang, 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 and then like this, okay? But you will see that this one does not satisfy this property, although there is a path in that where with T naught being repeated, you can, and T1 repeated twice, T2 repeated twice. Now, I've chosen this such that you will have to consider extensions of paths from each of these states, okay? Therefore, if that is the worst case, for this X, so you could look, if all you have in your formula is F, single F and multiple X's embedded, you can kind of count the number of X's, okay? And then, and that times the recurrence diameter can be the bound, okay? That is, so you will have to see the structure of the formula, okay? And what is the worst case repetitions of paths from the path corresponding to the recurrence, non-repeating lasso that you take, then you will have to do it. So that's how you have to analyze, okay? And this has to be done on a property by property basis, or like I said, the one paper that I referred to, which had the thing, has certain classes, subclasses of LTL properties that satisfy certain structure. They call it clique, whose graph representation satisfies certain clique properties, can then admit these kinds of linear function over the recurrence diameter and the diameter. And these are some cases like that, yeah? And that's why you will have to analyze that, the embedded X's in this case, to determine the bound. Okay, so I mean, the key takeaway here is, I want you to understand why, unlike for FP and GP, the recurrence diameter is no longer the bound. Okay, I hope you understand that. Okay, and that I hope, I mean, I've shown. And the other thing is when you have to get the worst case for such properties, you will have to look at the number of x's, and then you will have to, at least for single f or g embedded with certain number of x's, you take the worst case x and take that, multiply that by the recurrence diameter. Okay, so yeah, in general, when your embedded predicate inside G or F itself has other operators, especially x's, the recurrence diameter is no longer the bound, and it has to be something larger than that. Any questions here? I hope you're convinced of those two key takeaways that I wanted to convey. Any questions? Yeah, but the good thing is that you're still able to derive the bound as a linear, some linear function of the recurrence diameter.
So this happens because like the shortest example path would have multiple repeating states even within the lasso, right?
Yeah, that's correct. Okay, you will have to consider some, yes, some repetitions, correct? Because otherwise, if the smallest, I mean, if the smallest counterexample smallest, let's not keep saying counterexample, okay? Because we have reduced. I know it's a counterexample when you start with GP, okay? That kind of creates confusion, because now we are looking at existence, witness to existential LTL for any, okay, property, okay? So the smallest part for, as a witness to an E LTL formula, if it can be shown without repetition, you know, a lasso without a repetition, then you will get, before the recurrence diameter, okay? If you have to consider repetitions, then, you know, you will have to look beyond recurrence diameter, correct? Yes, that is one way to look at this, yes. But an interesting thing is, look at this. So what do you think? So I have G of F of P, F of G of P. Okay, these are very commonly occurring formulas, okay? Because with unary LTL, that's a fairly big class. I mean, you can express lots and lots of very interesting properties, okay? I mean, in real life, you don't need very deeply embedded FP&GP, but maybe you could. But certainly, a lot of the properties can be expressed as GF of P, which is something happen infinitely often, or F of G of P. So what do you think is the I'm already giving you. So even though you have a nested temporal operator here, it's still the recurrence diameter. Yeah. Question there? Was there a question?
No, sir. I was thinking about this problem for a while, and I thought I got answer.
Which program?
No, this problem only. GFP.
Okay, good. Let's take GF of P.
Both of them are right.
Huh?
Both of them are correct, right?
Say that again.
For both of them, recurrence diameter is a bound.
Correct. But what is the argument? Is what I'm saying.
So what you can do is there will be a path which will eventually lasso. So what happens is there might be some other loops in the path which are not the lasso part, right? So the thing is that we can remove those loops, and in the end we'll get a path that lassos without any loops, and its length will be at most the length of.
Yeah, that's true. That is the argument you give for G of. I mean, that is for FP and GP. But
because
I mean, why is the reason that you can remove? Because see, in the case of X, when you had X like here, you were not able to remove, right?
So here what we can argue is, here the properties mean that GF means that P occurs infinitely often, and FGP means that after some point of time it globally holds true. So these two
Okay.
properties are key in the proof.
Yeah, I mean, it's a, yeah, I guess, you know, you're getting, it's really because of the P. Okay. So let's suppose, just look at G of something. Okay? Yeah, you may be right, but the formal argument, you know, can be a little bit more precise. It is something like, you know, as follows. It's really following because it's a predicate. Embedded thing is a predicate here. So let's look at G of P. What is the bound? If you had G, I mean, it is the recurrence diameter. Okay. Let's suppose that the recurrence diameter is not the path, the minimum path that you require to show as a witness to this is longer than the recurrence diameter. Why would that happen? Because you, of course, see, when you have that, you know, the path that on which all states are different. Okay. Now, if obviously that is not a witness to G of F of P, why would it not be a witness? Because then some path, like for example here, say this is a path, okay? This is a, you know, for this transition system, this is the longest path that is, you know, that you can go. So if this is cannot be a witness to G of F of P, what that means is there must be some state, one of the states here, from which there is a path. I mean, this path itself, maybe not of P, not of P, not of P holds good. I mean, for the moment, okay, although that's not the case here. So let's suppose that every state here is not of P, okay? So that is not a witness to G of F of P. So you must look, there must be a path. If there is still a path, a witness to G of F of P, there must be some path from any one of these states that it goes and then lassos, okay, on which P is true in one of the states, okay, because it's the OR of that. Now, if that is smaller than this, you would have already encountered. If that is larger than this, then how could it be? I mean, if it is something that is going from here or something, you know, so if it is larger than that, in the sense, if it is larger, then it must have, like there, Kapil, your argument is applicable, because if it is larger, then you know, then it should have repetitions, because if it did not have repetitions, then that would have been, this would not have been the path exhibiting the recurrence. This would not have been the recurrence diameter. The recurrence diameter itself would have been bigger, okay? And why should that, any path from one of these states, you know, that exhibits going to a P, cannot have repeated states? That is the most important thing. That's also an equally important thing. That's because you only have P, okay? Because you don't need, if you have just a predicate, you're just taking on any path to show FP, you're just taking a disjunction of those paths. So if there are repeated things, you might as well remove that, because that is not contributing to violation of, that is not contributing to showing the existence of P. Therefore, you could remove that, okay? So that's why. So the important thing is, because the embedded thing is only simple predicate on state, you can check that FP on a path in which you take the disjunction of the things, and then for which you don't need to consider repeated paths, okay? Paths that have repeated states. And such paths should have already occurred before the recurrence diameter, even if they are originating from any of these states. Otherwise, this would not have been the recurrence diameter, okay? And that's how you do. You can show by contradiction, okay, that as part of which you will use two important things, okay? The one, the argument that, okay, the repeated paths is not needed, that Kapil pointed out. And the other one is, if it is, if there exists a path that is longer to show its eventual reaching P, then that itself would be the recurrence diameter, and it would not be this one. Okay, and that's how you could show. So for both these things, recurrence diameter is good enough. Of course, if you have x's here and x in between, then it is something more. Okay, and then you will have to kind of analyze and see what is the multiplicative factor that, in the worst case, that you will need. That is a loose bound. If you want a precise bound, then that's quite hard. But I think in this methodology, expressing some loose bound as a linear function of recurrence diameter is the most reasonable thing that you can do, because I mean, computing anything else like diameter is very hard. I mean, it's not possible. Even recurrence diameter is possible only for small systems. Okay, so for GF, FFP and F of GFP, it is yeah. So I want to stop here. So good. So yeah. So you will get the satisfaction. The reason I'm quite yeah, whether you guys are excited about the project or not, I'm excited about the project, because the first time I'm doing kind of a complete thing. I mean, I've usually done this in the past, but here I've done it kind of complete. If you'll be implementing the recurrence diameter, you'll be implementing it for the full LTL, and you will have a complete system, okay, that you will have the experience of building using SAT. And I think that is, I hope that you will enjoy and you know, will be a learning experience. Okay, and please get your partner involved in the task, and you can tell them that I'm a bit disappointed that not everyone is here. And I know Diganta, who's your partner? He's not here.
Yeah, he's.
Well, Shivang rarely shows. Maybe he listens to the thing. I don't know. Kapil, your partner is?
I'm me, Arpati.
Ah, okay. So you guys are good. Rishikesh, you are partnering with whom?
Shivang.
Who? Shivang. Oh, Shivang is someone who's not here at all. So I hope you are.
I think he listens to the YouTube stuff.
Yeah? Oh, he listens to the YouTube, is it?
I mean, I think so.
Ah, okay. No, that's okay. So that is fine. But you know, you will have to feel confident. That's why I'm giving you, you know, bits and pieces of the inside information as to what you need to do in implementing each of the tasks that I've listed. Okay, and so it's I'm not giving, you know, leaving it completely to the dark. Okay, and so you know, with that and with the effort of another person, I certainly think you should be able to do it. What I have not done yet is I have discussed in the class, I have not gone at this level of detail into implementing a SAT procedure, SAT-based procedure for deriving the recurrence diameter. Once again, I ask you to think about it, at least, you know, before I give you pointers to how it is. I want for you to think and put some effort to at least thinking about the problem, so that you know, I would be happy that you put in, you know, without, you know, short of my giving the entire solution to you. Okay, and I want that be done. Okay, so any questions?
For the this project, have you is the there was a text file listing exactly in details what we need to do, right?
I will upload it. I haven't uploaded it. This one you're talking about, right?
Yeah.
Okay, so I will upload this. Yes. Okay, guys. Thank you. See you next week. Bye-bye.